Yes, we are good to go. Poof. Excellent. All right. Any questions?
Yeah. All right. Thanks. It's about number 1, and when it's asking for a real-world example of two faculties we discussed, what faculties are you talking about?
Which? This is a homework question?
Yeah, homework 1. Yeah.
Define propositions P and Q and use them to give real-world examples of two fallacies we discussed. The fallacies are denying the hypothesis and affirming the conclusion. So we have two laws of logic, which are not fallacies, but are in fact, laws of logic. And one of them is called detachment, and it looks like this. Given P implies Q and P, we can conclude Q, so that's detachment or direct reasoning. And then we have indirect reasoning, which looks like this. If P implies Q and Q is false, then P is also false. So those are valid laws of logic. But then there's two things that look similar to that, but are actually not laws of logic. They're called fallacies. And so one of them looks like this. P implies Q, Q, therefore P. And that's a fallacy and what we're doing here is affirming the conclusion. And if P implies Q and Q is true, that does not mean that P is true. Right? For example, if I'm an evil, mean teacher, then I drink water every day. I drink water every day, therefore I'm an evil, mean teacher. Right? So it doesn't go in that direction. So when you state that the conclusion is true and therefore try to say the hypothesis is true, that's a fallacy. And it's called fallacy of affirming the conclusion. And the other fallacy is denying the hypothesis. And it looks like this. So here we say if P then Q, but P is false and therefore Q must be false. So fallacy of denying the hypothesis. If I win the lottery, I'm going to give you a midterm on Friday. That's a true statement. Next Friday. I don't win the lottery, therefore I don't give you a midterm. Well, that doesn't follow logically. You're going to get a midterm whether I win the lottery or not. So those are the two fallacies. So for question 1 on the homework, I just want you to give me examples similar to the ones I just gave, but something, that this is clearly true and this is true, but this is not true. Where these two things are true, but this is not true. Does that make sense?
Yes, thank you.
Alright, you're welcome. So go ahead and send me an attendance ping. Let's see who's here. And attendance is dropping off. I don't know what the deal is. It's weird. My 10 o'clock 224 class is close to perfect attendance, and the 11 o'clock is dropping off, and this class is dropping off. I might have to gamify it. Alright, any other questions like on the homework or anything else?
You just answered mine.
Cool. My question would be, where are my glasses? But I'll find them sometime. Oh, there they are. Alright. Alright, well, let's keep talking about number theory and things related to number theory. And I think we left off last time talking about primes. And who remembers the definition of a prime number?
A number that is divisible by 1 in itself and nothing else.
Exactly, yeah. So 2, 3, 5, 7, 11, 13, and so on are prime. 6, 9, 25, 32, these are not prime. And if it's not prime, it's called composite. Oh, physics midterm, good luck. Anybody who's got their physics midterm today, good luck with that.
Yeah, I got one too. Got two.
Yep. These things happen. Physics was not a good subject for me in school, but I'm glad I took it. I think by the time I was done with physics, it had taught me some things about breaking down problems and restructuring problems, and I think it's some stuff I actually use as a coder today, even though I don't remember F equals MA.
Well, it's funny because I'm getting the material and I'm totally understanding it, but the teacher has us doing 10 decently hard, it's multiple choice, but 10 calculated problems over 15 minutes
Oh wow.
for the quizzes.
Mm-hmm.
So I'm not doing great on those. I'm like averaging probably about 70% on those.
Okay.
It doesn't make me very happy. I'm a straight A student, so it kind of pisses me off.
Yeah, it's like a minute and a half per question. That doesn't seem like a lot of time.
Yeah, it's kind of set me up for failure, I think, but
My modern physics class, I kind of made a deal with myself that if I passed, I was going to switch and be a major in physics. And I passed by like 4 points. Passing was like a 40, and I got a 44, so technically I passed. And I was like, yeah, I don't want to do physics though, so I broke my deal with
I
myself.
think it's a fun, cool subject and cool information, but I'm hoping to get into UW so I don't have to take anymore.
Ah, right. All right, so prime numbers, right? Primes are these things that are only divisible by themselves in one, and you know, we have ways to tell if something's prime. We can try dividing by things other than itself in one, and so trial division, and we can write a computer program to do that by just, you know, keep dividing, see if there's anything left over. There's the sieve of Eratosthenes that we looked at, where you write out all the consecutive numbers and you start crossing out every other, every third, every fourth, every fifth, and what you're left with are prime numbers. And we talked about the fundamental theorem of arithmetic, which talks about factoring things into primes. And you know, if something is not prime, then it's divisible by something other than itself in one. But in particular, it's divisible by prime numbers. And so, for example, 1001 is 7 times 11 times 13, I think. Let me double check that. I should know that one. Yeah, 7 times 11 times 13. So there's this theorem that we can take any number that's not prime and write it as a product of primes. And you know, sometimes it's like 32 is 2 multiplied by itself 5 times. But you can always break it down into this. So prime numbers are in some sense like building blocks of other numbers. They're kind of like atomic units, and that also makes them interesting. So a question that the Greeks considered and found an answer to is, you know, how many prime numbers are there? And who knows the answer to that? How many primes are there? It's an infinite number. And it gets harder and harder to find primes because, you know, if you get up to a really big number, there's a lot of things that could potentially divide it. And so chances are, if you pick an arbitrary, you know, number with 100 digits, it's probably not going to be prime. But to prove that, you know, you have to keep dividing it by things and find a factor. And to prove that something's not prime, you'd have to divide by all the primes smaller than it, and that's hard. But even though the primes generally seem to get harder and harder to find, there's an infinite number of them. And that's really not too bad to prove. And this is a good example of a proof by contradiction. And a direct proof is really hard, trying to directly prove that there's an infinite number of primes. But let's do a simple proof of this theorem. There is no largest prime number. And our proof, we'll do a proof by contradiction. So we'll negate this, and we'll say there is a largest prime number. And that's the negation of this thing that we're ultimately trying to prove is true. And I'm not going to make this terribly formal. I just want you to see kind of the idea of how this works and how the indirect approach works so easily. So if we suppose there is a largest prime number, well, that means there's a finite number of primes. And let's call these primes P1, P2, P3, all the way up to Pn. So let this be the set of all prime numbers. Alright, that's our assumption, and we're going to argue to a contradiction. And the contradiction is really easy. Let's just let B, for bad, be the product of all of these, plus 1. So I'm making a really big number called B, and it's the product of all primes plus 1. And now we ask the question, is B prime? And it can't be prime. This number is certainly bigger than any number in here, right? I mean, it's certainly bigger than Pn, which is the largest number in here. So B is not prime, which means it must be divisible by something other than itself in 1. And by this fundamental theorem, it must be divisible by a prime number. But you can see that this number cannot be divisible by any of these primes. In fact, it's 1 more than a multiple of P1. It's 1 more than a multiple of P2. It's 1 more than a multiple of P3, and so on. And so there's a contradiction right there. Right? This big number can't be divisible by any prime, which means it must itself be prime. But it can't be prime because it's bigger than all of the primes in this set of all primes. So you quickly hit a contradiction, and your only conclusion is that this statement must be false. And so there is no largest prime number. So the Greeks knew this proof. Probably people knew it before the Greeks. And so we can keep going. We can keep finding more and more primes if we work hard enough. But the primes tend to thin out. So you start off with, 2, 3, 5, 7, 11. And, here's a distance of 1, here's a distance of 2, 2, 4, here's 13, 17, 19, 23. So there's a distance of 2, 4, 2, 4. Our first, half dozen or so primes are all separated by like 2 or 4. So they're pretty close together. When we go from 23, we jump up to 29, there's a gap of 6. But we quickly go back to 31, and then 37, and 41.
They prime out once you hit like 10 squared, once you hit 100.
They start thinning out once you hit 100. They're starting to do a little thinning here. We got some gaps of 6, but we're back to like gaps of 2 or 4. But as they get bigger and bigger, that distance between primes tends to get larger, but not consistently. And one thing that's interesting is that seemingly no matter how far out we go, we get to 101, well, it turns out 103 is also prime. And so there are these things called twin primes, which is where you have 2 odd numbers in a row that are each prime. And it turns out that no matter how big a number you look at, you always find twin primes bigger than that number. And we don't know if that's always the case, but through observation, so far that has been the case. And we don't know why. Because, I mean, the distance is getting further and farther apart in general, but you still find, you know, primes that are really close to each other. So that's an odd little fact. All right, so by observation, yes, all prime numbers are odd except for 2. 2 is the oddball, no pun intended. And this is because any other even number is going to be divisible by 2, because that's what an even number is. It's something that's twice an integer. In the same way of thinking, 5 is the only prime that ends with 5. Because any number that ends with 5 is divisible by 5. 15, 25, 35, 45, 105. And so these kind of feed into this idea that primes get generally further apart the further out you go. But it's not a uniform change in distance, because we still come back to these twin primes sometimes. But this raises an interesting question, which is how many primes are there below any number n? So I could say, how many primes are there that are smaller than 100? How many primes smaller than 1,000 or 1,000,000 or 1,000,000,000? And this leads to something called the prime number theorem. And this is a wonderful theorem that really shows you that there's something weird going on here. So so how many people here have looked at natural logarithms? It's like log of x. Raise your hand or give a shout or ping a message if you've seen this.
The graph?
Just the function itself, how many people have heard of it?
Oh yeah, that's pretty big in calc too.
Okay, cool. So this is the log base e of x. And it's the number that if you raise e to that number, you get x. And what is e? It's this thing that's, you know, 1 plus 1 plus 1/2 plus 1/6 plus 1/24. And it's this sum of reciprocals of factorials. And it's this thing that if you look at e to the x and you take the derivative of it, you get e to the x. And if you take the integral of e to the x, you get e to the x. So it's this thing that changes at its own rate. It's all this calculus-y type stuff, right? And so E, you know, pops up in nature and studying snail shells and bacterial growth and all kinds of stuff like that. And logarithms base E, that's this natural log. What turns out, if n gets really big, the number of primes less than n is approximately the natural log of n. And as n approaches infinity, this becomes more and more exact. So we don't need to know what natural logs are. That's not really part of this course. But if you know it, it should kind of startle you that this weird constant, right, which has this property with respect to derivatives and integrals, and this logarithm base that constant describes how many primes you get up to a large number. And that's a wicked proof. There's a bunch of ways to prove that. And that's a springboard to lots of weird mathematical areas. But that's the prime number theorem. And if we wanted to write this more formally, we could do something like this. The limit as n approaches infinity of number of primes less than n divided by log of n is equal to 1. Internet troubles, yay. I lost my internet the other day, it was weird. That hasn't happened in a long time, it's just gone. Alright, so that's the prime number theorem. Number of primes less than n is about log n. You gotta get really big for that to become obvious. I mean, it starts off and it's nowhere near that. But, you know, picture n approaching infinity, that becomes an exact approximation.
That is insane.
Yeah, I think it's pretty freaky. Alright, let's talk about another interesting open problem in, so this we know, this has been proven. Here's a problem that's a lot simpler that has not been proven. This is called Goldbach's conjecture. And so let me write this as a question. Can every even number bigger than or equal to 4 be written as the sum of two primes? And Goldbach's conjecture says the answer is yes. So for example, 4 equals 2 plus 2, 6 equals 3 plus 3, 8 equals 3 plus 5, 10 equals 5 plus 5, it also equals 3 plus 7, 12 equals 5 plus 7. And, you know, as far as you can go, you seem to be able to do this. It might take a while to come up with the right combination, and I think this is the only combination of primes that adds up to 18, but there is at least one. And so the question is, can you do this forever? Or is there an even number that's not expressible as a sum of two primes? And it's an open question.
If that's true, doesn't mean that there's like a definite formula for finding primes?
Not necessarily. And we're not asking, is there a formula for writing even numbers as a sum of two primes? We're just asking, is it possible? And asking if there was a formula, that would be an even harder question. But this is a simpler question, just is it always possible to take any even number? Can it be written in some way as a sum of two primes? And nobody knows the answer. And so this is a very old question, and it's another one of these questions that if you can explain to someone what a prime number is, and what an even number is, and what addition is, they can understand what this question is asking. And, you know, it's so simple to state, but really, really surprisingly hard to solve. So I'm looking at a Wikipedia page right now. And so in 1938, one person proved this up to 10 to the 5th by hand. So they proved it up to, you know, 10,000, 100,000. And let's see. Now I'll just bring this over here. So it's been proven for all numbers up to 4 times 10 to the 18th, and double checked up to 4 times 10 to the 17th. And this is the smallest even number that cannot be written as the sum of two primes, or one is smaller than 9,781. Why, I don't know, but so you know, if you only work with 4-digit primes, you can do all numbers up to and beyond this large number, but can't prove it, can't disprove it. And there's some interesting graphs here. So number of ways to write a number as a sum of two primes. So there's a few numbers that can only be written a few ways. But we have this kind of banded behavior where, you know. So this is weird stuff, right? And it's pretty typical of the field that you can make a simple question like this, and it can lead you into like so many interesting areas. And some of that we understand, some of it we don't. So that's Goldbach's conjecture, and I think one of your programming assignments for this course is going to be to write a program that will test Goldbach's conjecture. That will basically take an even number and tell you how to write it as a sum of two primes. And we'll just do that by, you know, exhaustively trying different values.
I've made a bunch of programs about prime numbers and trying to calculate a certain given number.
Yeah.
I think it'd be interesting to try it with log now.
Cool.
Like find the approximation, then work up from there to find the next prime.
Yeah, definitely. And I can't explain like how rich these questions are, but if you really want to lose yourself in some reading, take a look at the zeta function and something called the Riemann hypothesis. And this is related to distribution of prime numbers and density of prime numbers. And this is like the end of common sense as we understand it, and they're closely tied into each other. And that's just, you know, if you decide you don't want to do physics anymore and you want to just like rebel and go off down a rabbit hole, those are fun rabbit holes. All right, so that question. All right. So one more thing to talk about with primes. This is Mersenne Primes, and this is a particular type of prime number. And it ties in nicely to computer science. So the number 3 is prime, and this is actually 2 squared minus 1. And if you have a power of 2 minus 1, what does it look like in binary? Looks like a bunch of 1s side by side. A 7 is also prime, and that's actually 2 cubed minus 1. So that looks like 3 1s side by side. I'll put a little base here, let you know it's binary. 2 to the 4th minus 1 is 15. Well, that's not prime. 15 is 5 times 3. But 2 to the 5th minus 1, that's 31. And that's 5 1s side by side. So far so good. 2 to the 7th minus 1. Well, 2 to the 7th is 128. Subtract 1, you get 127. That turns out to be prime.
I'm seeing a pattern. It looks like it's just like 2 to a prime minus 1.
Yeah. This looks like if you take 2 and you raise it to a prime and subtract 1, maybe you get a prime number. And if you wrote that in binary, it would be P1s side by side. So these are called Mersenne primes. They're primes of the form 2 to a power minus 1. And it turns out for this to be prime, your power has got to be prime. If P is not prime, 2 to the P minus 1 won't be prime either. And that's provable. But it turns out not all Mersenne numbers are prime. And the pattern breaks at 2 to the 11th minus 1. So 2 to the 11th is 2048. This is 2047. Looks like that in binary. But it's got a factor. I don't remember what the factor is. So 23 times 89. So that kind of breaks the pattern. But nonetheless, these are really interesting numbers when they are prime. And so in the quest for finding large prime numbers, people have looked at numbers of the form 2 to a prime minus 1. And a lot of them turn out to be prime. And so there's 51 known Mersenne primes right now. So there's the first few. 2 squared, cubed, 5th, 7th. 2 to the 13th gets you back to a prime, and so on. So these first few, under discovery, it says ancient times. 2 to the 13th was 1456 by someone who wished to remain anonymous or simply wasn't known. And then this person found 3 of them, right? And so the number of digits in the prime, well, this is a 6-digit number. And then you skip ahead a couple of hundred years to good old Euler, and he found 2 to the 31st minus 1 was prime. And that's a 10-digit number. So that's a little harder to prove. And then you go forward about another century to late 1800s, and there's another one. And then 1900s things start getting interesting. So 1876, Lucas found 2 to the 127th minus 1 was prime. That was before these were discovered. But this itself is a Mersenne prime. And so when you raise 2 to a Mersenne prime power and subtract 1, you've got some extra stuff you can say about that. And one of the things Lucas did was he came up with a test for primality. Today it's called the Lucas-Lehmer test. And it's a way to test to see if a Mersenne number is prime without having to divide by every prime smaller than it. It gives you a more nuanced approach. So not much happens until we get into the middle of the 1900s. And we find a few more Mersenne primes, and we're up to several hundred digits at this point. And then computers are starting to come out, and people are starting to code these things on computers and so on. And let me get the source of this. So these were done by trial division. This was using Lucas sequences. That's the Lucas-Lehmer test. And then in 1900, so this was the first Mersenne prime I learned about when I was a kid. This was the one I memorized, like that exponent. And Guinness Book of World Records would publish these every year. And these were all done by Lucas-Lehmer test, right, using computers. But when you look at who discovered these, something interesting happens in the mid-90s. This was discovered by something called GIMPS. And GIMPS is the Great Internet Mersenne Prime Search. And this was a crowdsourced program of trying to find large Mersenne primes. And you could download a screensaver for your computer, and when your screensaver would kick in, it would actually be running a Lucas-Lehmer test in the background, testing a new possible Mersenne prime. And these started being how we discovered prime numbers from the mid-90s onward. And some people, their names will pop up multiple times because they probably had lots of hardware running on these things. But by and large, this is where the primes were being discovered. And it was crowdsourced, right? And crowdsourced distributed problems, they pop up all over the place. SETI, Search for Extraterrestrial Intelligence, had a SETI at Home program going through the 90s where you could analyze radio telescope data, and it would look for signatures of life. With COVID, there's code you can download and run in the spare cycles on your PC that will search for medicines that react a certain way with these viruses and so on. So this was a crowdsourced approach of finding prime numbers. And the last Mersenne prime discovered was December 2018. So we're way overdue for a new one. And that had almost 25 million digits to it. So these are big numbers, and they're definitely not being tested by dividing by every number below it. They're using this thing called a Lucas-Lehmer test. But there's people all over the world running this in the background on their computers, and every now and then somebody finds a new prime, and you get your name up on the Mersenne Prime page. So that's Mersenne numbers and Mersenne primes. All right, so let's go in the other direction and talk about things that are not prime, things that are divisible by other numbers. And one thing that's interesting for us, and this will be interesting for crypto and such, is looking at common factors between two numbers. So for example, you might have the number 75 and 36. And you know that neither of those are prime, but you might say, is there a number that divides both of them? And is there more than one number that divides both of them? And in particular, what's the largest number that divides both of them? And one way to do this is to write this as a product of primes. So this would be 3 times 5 times 5. And this would be 2 times 2 times 3 times 3. And we only see one thing in common between these, that's a single 3. And so we would say the greatest common divisor of these numbers is 3. And we use GCDs when we're learning about fractions. If you want to make a fraction like 75/36, but put it in simplest term, what do? Divide the top and bottom by the greatest common factor. And this would become 25/9, and we can't simplify that any further. So someone suggested in chat that organizations interested in crypto could sponsor prime number lotteries, and people get a little payout by finding large primes. You can actually do that. That's kind of what Bitcoin mining is all about. To make cryptocurrencies work, you need big primes, numbers with certain properties, and people will run searches on their hardware to try to find numbers with these required properties, and they're getting harder to find because the more cryptocurrency you generate, the more you use up these numbers. So Bitcoin mining is, sort of sifting through the maze of numbers, looking for these little nuggets of gold, these numbers that can be used for making cryptocurrency. And it was funny, it was about 7 years ago, service learning project, the year-long project that we do through the CS sequence, all of a sudden, like about a quarter of my students wanted to do Bitcoin mining for their SLP. And it's like everybody sort of converged on it at the same time. And this is why sometimes there's like a GPU shortage, because there's a new way to make money by, mining for numbers, and so everybody buys up GPUs not to do graphics, but to use the GPU hardware to do number crunching, to do things like mine for Bitcoins. So yeah, this
is actually pretty smart. I wish my SLP was to pay off my tuition.
Hey, there you go. Yeah, if you could come up with like a lottery program, that would be cool.
Yeah, unfortunately, Bitcoin is so expensive now. Unless you have like hundreds of GPUs mining at the same time, it's not really worth doing.
Yeah.
You don't get paid out enough.
Mm-hmm. Yeah, it's a weird. And I almost bought like $20 in Bitcoin like right before it took off, just because I saw an ATM and I thought, well, this is kind of cool. But I was in a rush, so I didn't do it. Yeah, these things happen.
See, I mine a coin called Shiba Inu. It's worth very little right now, but it's getting some traction, so I'm hoping
Oh, cool.
a few years from now it's the new Bitcoin.
Yeah, totally.
My dad and I used to do transactions in Bitcoin just when it was across the country and stuff.
Oh, wow.
For materials, and back when it was like $40, we had like $2,500 in Bitcoin.
Wow. Yeah, that would be nice to have today. All right, so yeah, so greatest common factors. So we can write these numbers out as products of primes, but there's an algorithm we can use to find the greatest common factor, and it's called the Euclidean algorithm. I'm blanking on how to spell Euclidean. That does not look right. I'm going to spell it. Hold on. Yeah, I spelled it right. All right. So this is an algorithm that's really easy to teach a computer how to do. It's a little harder for us to do it as humans, but it translates pretty well to a computer. But let's look at this in some examples. So 75 is one number, 36 is the other. So the first thing you want to do is write 75 as something times 36 plus something. So how many times does 36 go into 75? It's going to go in twice. It's going to leave us 3 left over. So this will be 72 plus 3. Alright, now we ignore that 2, the number of times it went in, but we take the 36 and carry it over here, and we take the 3 and we carry it over here. And now we write 36 as something times 3 plus something. So 3 goes in exactly 12 times, we have 0 left over. When we get to 0 left over, this is our GCD. Alright, let's do it with a few different cases. So let's do 735 and 252. Alright, so 735 equals something times 252 plus something. So 252, you got to use a calculator to figure these out usually, but 252 goes into here twice. That'll get us 504 plus 231 left over. We ignore this 2 here, but we carry the 252 over here and the 231. So 252 is something times 231 plus something. So 231 goes in once, and this leaves us 21 left over. We ignore the 1, we take the 231 over here. Something times 21 plus something. And it turns out 21 goes in exactly 11 times with 0 left over. Once we've got the 0, this is our GCD. So 735 divided by 21 is 35, and 252 divided by 21 is 12. So if we were writing this as a fraction, it would be 35 twelfths. That's really all there is to it. What phone app is that? Let me see. That is RealCalc. It's been my favorite calculator program for a long time. I should give them some money. But it does like, you know, all the usual scientific stuff, but you can also like put it into hex and, you know, do like ABC and convert it back into decimal and so on. And it does binary and everything else. All right, so that's all there is to the algorithm, and it works in all cases. If you happen to use this backwards, like if you tried to find the greatest common divisor of 252 and 735, Well, you would start off by saying 252 equals something times 735 plus something. And 735 goes in here 0 times, and how much is left over? 252. And then when you carry this down, you get 735 equals something times 252 plus something. And hey, you're right back at this step. So if you code this in the computer, it actually kind of works, even if these things are in the wrong order. And if one number is a multiple of another, for example, if you wanted to find the greatest common divisor of, I don't know, 28 and 7, well, you would say 28 equals something times 7 plus something. Well, 7 goes in 4 times with nothing left over. There's your greatest common divisor, which is how it should be, right? Because 7 divides this and 7 divides that. And if you have a pair of prime numbers, you're guaranteed the greatest common divisor is 1. Because, you know, unless the numbers are the same, the only thing that's going to divide both of them in common will be 1, because that's, you know, one of only 2 things that divides each number. So greatest common divisor of, say, 23 and 7. So we could write 23 equals something times 7 plus something. Well, this goes in 3 times with 2 left over. 7 equals something times 2 plus something. Well, this goes in 3 times with 1 left over. Take the 2 down. 2 equals something times 1 plus something. Well, 1 goes into 2 twice and you have nothing left over. Once you get to that nothing left over, there's your GCD. So when you have 2 numbers and the greatest common divisor is 1, we call those relatively prime. Now it turns out 23 and 7 are also actually prime numbers themselves, but for example, 25 and 4 are also relatively prime. This is divisible by 1, 5, and 25. This is divisible by 1, 2, and 4. The largest number that divides both is just 1. And if you do the same calculation, 25 equals 6 times 4 plus 1. 4 equals 4 times 1 plus 0. There's your GCD. And relatively prime numbers, again, are something that will pop up in crypto. And these super intense crypto algorithms that we're going to talk about are all about, you know, doing operations on mostly prime numbers. And they mostly center on the idea that multiplying primes is easy, factoring a number into primes is hard. So like that Mersenne prime that we worked with a little while ago, which was 2047, right? Factoring that into primes took a little bit of trial and error. Multiplying those primes to get this is you know, just pencil and paper multiplication. So GCDs will pop up and relative primeness will pop up in crypto. So you got some homework questions on doing Euclid's algorithm, and that always pops up on tests also, so that's good stuff.
You would use this to hunt for prime numbers also, right? If you find something that's relatively prime, you found a prime number?
Not necessarily. So for example, 25 and 4 are relatively prime, but neither of these numbers is itself a prime number. But they have nothing in common with each other. But sometimes it's useful to have things that are relatively prime. There's things we can say about numbers if they're relatively prime that we can't necessarily say if they're not. And we'll see some examples of that in a few minutes. Alright, so let me mention something called the Chinese remainder theorem. And I'm not going to go through the details of this, but I want to tell you what this theorem basically relates to, because it's another thing we'll use when we talk about crypto. So you've probably done simultaneous equations in algebra. You've done them in CSE215 when we do KVL, KCL. A series of equations with a series of unknowns. And you can say, you know, is there a value that satisfies all of these equations? For example, you know, 2x plus y equals 4, and x minus y equals -1. And can you find values x and y which satisfy both of these equations? And you know, if you said x equal to 1 and y equal to 2, well, 2 times 1 plus 2 is 4, 1 minus 2 is -1. There's a solution. So we can do the same thing working with modular arithmetic. We can say if we have a series of equations modulo something, can we find a solution? And so here's an example. Suppose I have some unknown variable x, and x is congruent to 2 modulo 3, and x is congruent to 3 modulo 5, and x is congruent to 2 modulo 7. What is x? And this problem pops up in a Chinese text that's several thousand years old, and so this is why it's called the Chinese remainder theorem, because it states this question and it gives you an answer to it. And one value of x for which this set of equations will be true is x is 23. It's 2 more than a multiple of 3, because 23 minus 2 is 21, and that's 3 times 7, right? It's 2 more than a multiple of 7, because 23 minus 2 is 21, that's 7 times 3, and it's 3 more than a multiple of 5. 23 minus 3 is 20, that's 5 times 4. So this is a solution. There's actually an infinite number of solutions, but this is the smallest positive integer for which all 3 of these things are true. And the Chinese remainder theorem is a theorem that lets us find this solution when it exists. And I'm not going to go through what that algorithm is, and you're not going to be responsible for it. But I want you to understand that there is a thing called the Chinese remainder theorem. It can be used to solve systems of equations like this. Alright, and then here's the kind of last piece of the puzzle, is Fermat's little theorem. And this is not Fermat's last theorem. This is a theorem that Fermat stated and presumably proved, and there are proofs for it. And they're relatively straightforward by people who do things like this. So here's Fermat's little theorem. As opposed to the big theorem that, like, you know, pops up in science fiction movies and stuff. So if P is prime and P does not divide A, then A to the P minus 1 is congruent to 1 mod P. Alright, so fix some prime P in your head. As long as A is not a multiple of P, A to the P minus 1 is 1 more than a multiple of P. If A itself is a multiple of P, then this, you know, A multiplied by itself a bunch of times will also be a multiple of P, so this would be congruent to 0. But other than that case, A to the P minus 1 will be congruent to 1 modulo P. What section is homework 4 from? So this is number theory. It's discussed in that alternate textbook that's posted on Canvas, but mostly it's material we're going over in lecture. So it's really just from the lecture material. So let's look at some examples of this. So I don't know, let's do P equals 7. And a can be any number that's not a multiple of p. So I don't know, p could be 10, a could be 10.
On our standard console, not the paper.
So p is 7, a could be 10. And so this theorem asserts that 10 to the 6th should be congruent to 1 modulo 7. So here's 10 to the 6th, here's 10 to the 6th minus 1, and here's 10 to the 6th minus 1 divided by 7, and it's a whole number. If we picked p equals 31, and a is anything that's not a multiple of p, so I don't know, 25, 27, whatever. Fermat's little theorem claims that 27 to the 30th should be one more than a multiple of 31. So let's look at 27 raised to the 30th minus 1. That's a big number. If we divide it by 31, it's a whole number. So it's kind of remarkable, right? Because a to the p minus 1, right? I mean, that can be a really big number. It's always one more than a multiple of p. And we'll make use of this when we do public key crypto. But this is also useful for doing large arithmetic in general. So Fermat's little theorem has its own applications. So for example, let's calculate 7 raised to the 222 mod 11. Alright, well there's a few ways to do this. One way is to multiply 7 by itself 222 times and then divide by 11 and look for the remainder. That's not a really efficient way to do this. Another way is to use modular exponentiation, which we talked about last week, where we write this number as, powers of 2 added together, and then we take 7 squared, 7 to the 4th, 7 to the 8th, we calculate each of those, and then add up the corresponding terms, right? That whole thing we talked about last time. But sometimes Fermat's little theorem gives us a faster way to break this thing down. So if you're asked to calculate something like this using Fermat's little theorem, a good first step is let's think about what Fermat's little theorem says and see how this might relate to this question. So Fermat's little theorem, remember, is telling us something about a to the p minus 1 mod p. Well, we're trying to calculate, something to a power mod 11, and 11's prime. So let's see what we can state using Fermat's little theorem if we let p be 11. So FLT says a to the p minus 1 is congruent to 1 mod p. If we let p be 11, this tells us a to the 10th is congruent to 1 mod 11. Any a that's not a multiple of 11. So let's set a equal to 7, and without doing any work other than writing down what the theorem tells us, we have this really cool fact already, which is 7 to the 10th is congruent to 1 modulo 11. Alright, well we're trying to get to 7 to the 222, and we're only at 7 to the 10th. That may not seem like a lot of progress, but 1 is a really cool number. Because I can take 1, I can square it, I can cube it, I can raise it to the 22nd power, and it's always just 1. So if I can somehow get my 7th to the 10th to look something like 7 to the 222, I'll get my answer. Well, if 7 to the 10th is congruent to 1, I can square both sides and get 7 to the 20th is congruent to 1. I could cube both sides. I could take the 4th power of both sides. I could take the 5th power of both sides, right? And the right side is just, 1 raised to a power, that's always going to be 1. But my left side is quickly going up, right? And if I just, jump ahead and I say, let's take 7 to the 10th raised to the 22nd power, that should be 1 to the 22nd power, which is still just 1. This is all mod 11. What is 7 to the 10th raised to the 22nd? Law of exponents, right? X to the a raised to the b is the same as x to the a times b. So this is 7 to the 220th. Well, I'm trying to find 7 to the 222nd. I just jumped all the way up to 7 to the 220th. So I can multiply by 7. That's going to be congruent to 1 times 7, which is just 7. And if I multiply by 7 once more, that's going to be 7 times 7, which is 49. What's 49 divided by 11? Well, 11s are nice. 4 times would be 44. So I can get up to 44, and I've got 5 left over. So this is congruent to 5. And there's your answer. And we can double check. So there's 7 to the 222 minus 5. That's a nice number. And if I divide by 11, it's a whole number. Right, it's all zeros after the decimal point. So that's Fermat's little theorem. Alright, are you still with me?
Yeah, that's pretty cool.
It's a nice little trick. Alright, so let's talk about some general applications for all this stuff. And so we've touched on a few of these already. We talked about hash functions, the idea of doing like an MD5 hash. So you have a binary file with a few million bytes inside the executable, and you want to validate that this is the same file that you intended to download, that somebody hasn't replaced it with another file or changed some code inside to add something malicious. And if you had a copy of the original file, you could compare it byte for byte with what you downloaded and confirm that it's the same. But where would you get that copy from, right? Unless you downloaded it from a trusted source. So what we do is we have something called a hash function, and it takes this collection of, say, 1 million bytes, and it turns it into a little 512-bit number. And it does it in a way that if you made a change to that original file, you would get a different 512-bit number. And so that's a basic hash system. And so now on the website, right, that you're reading about this program you want to download, they'll show you what this 512 bit code should be, right? And when you download the program, you run it through something that generates the hash function for the file you downloaded, and you can compare those. So hashing is a topic for CSE215. We'll develop some hash functions and use them. But that's one application of this, and the algorithms for generating these hashes are, number theoretic in nature. You do simple operations, but you reduce modulo something. Really, example would be, just add up all of the bytes and reduce modulo 256. Right? That gives you something called a checksum. It's easy to foil, but it's a quick sort of first order way of detecting if something has changed. So if we forget about malicious intent and we think about just sort of data integrity in general, before internet was a thing, there were bulletin boards and there were things like Usenet and stuff like that, and these were sort of ad hoc networks that were created from computer to computer, and this was built on top of plain old telephone lines. And you could repurpose your home phone to send information from a computer in your home to a computer at school, for example. And you could log into school and do your work. And this was somewhat error prone. The earliest versions of this used sound, audible tones, and sent them, from your computer to a phone, and they would just transmit as audible signals. And it was a cool technology, but it was, somewhat error prone. So these acoustic couplers, right, you would dial up the number you were trying to connect to, and you would put the handset into these two sort of suction cup things that would, give you some kind of sound barrier, and sound would come through this end of your telephone. It would go into this microphone, and there was a speaker over here that would go into the receiver. And this was, how computers were connected to each other. Well, this is really error prone. If there was a loud noise, that would get transmitted along with the tones that were carrying the binary information, and your information that you sent might get corrupted. And worst of all, if you had two lines in the house and somebody else picked up the phone while you were in the middle of something, there'd be all kinds of noise, and it might be so severe you would lose the connection. So if you're sending information in this way, how do you know that the correct information is being sent? And so one easy approach is to use parity generation. And if you're using something like, an acoustic coupler where you're sending different tones to represent ones and zeros, when you send a character over, you send it one bit at a time. So if you want to send the letter A, that's got an ASCII code of 65. If we write that as an 8-bit number, it looks like this. And if you want to send a B, that's ASCII code 66. That looks like this. And if you want to send a C, that's 67. And that looks like this. And you have to agree, which part of the number are you going to send first. So maybe you just decide you'll start off with this bit first, the least significant bit, and you'll send this bit last. And so here's what happens, right? Say you're recording grades on a test, and I'm typing in, that somebody got an A on their test, and so that bit pattern starts being sent, but that first bit comes through, and when this bit gets sent, a car backfires outside, and the computer that's receiving it thinks that that's actually a 1. And so I sent an A, but the receiving computer saw the letter C. And now somebody's grade just changed. So how do you prevent this? How do you confirm when you receive this pattern that this was actually what was sent? And a pretty simple approach to do that is to add an extra bit called a parity bit. And so if you've done Engineering 250, right, there's a unit where we talk about Verilog, and good luck with the test, where we talk about Verilog, and part of what you do is you make a Verilog generator, a parity generator in Verilog. Right. So how does this work? We add one extra bit in the beginning or the end of our transmission, and if we say we're going to use even parity, we pick a bit so that the total number of ones we send is even. So we're sending 2 ones, and so we'll make our parity bit 0. Here we're sending 2 ones, we'll make our parity bit 0. But here the number of ones we're sending is 3, that's an odd number. So we'll make our parity bit 1. And so anytime we get a 9-bit number on the other side, we count how many ones we got and we make sure it's even. So what's going to happen if I try to send the letter A, but the car backfires down the road and this bit changes to a 1? When the computer receives it, it'll count the number of 1s and say, hey, there's only 3 1s. That's an odd number. There's a parity error. And it'll send a message and say, hey, resend that. And the sending computer will send it again, and hopefully the correct rate will go through. Alright, and this is just, add up those bits and reduce modulo 2. And if this is not equal to 0, that's a parity error. So that's a really, really minimalist kind of version of what a hash does. In this case, we're taking a byte and we're reducing it to a single bit, a 1 or a 0. And it's certainly not very secure because, for example, if both of these bits got changed to 1s, what's the computer going to do when it receives this? 1, 2, 3, 4. Oh, that's an even number of 1s. Hey, we're good to go. And it's not going to notice that there's an error. But with a little more effort and a little more modular math, you can start getting into things like ECC codes, error checking and correcting, where you can detect up to like 3 offsets, 3 errors in the bits, and you can actually start correcting some of those errors. So when you look online for computer memory, you can find memory that's slightly more expensive than the cheapest that says it's got ECC. It does this error checking and correcting. And it's a way to take 32-bit numbers and validate them. And it's just more, modular arithmetic, more gymnastics like that.
The newest memory has it built in.
Yeah. Yeah, it's on the chip. I don't know if they even still sell memory that doesn't have ECC, but it used to be you could buy less expensive memory that didn't have that.
Mine doesn't. You can buy DDR4 that doesn't have it.
Wow, that's amazing. Yeah, because when you're packing, multiple gigabytes onto, a little tiny substrate, the physical dimensions of the little capacitors where we're storing charge are so small, and the voltages are so low that the tendency for these things to be perturbed by, solar flares, stray alpha particles, things like that. I mean, that's just gotten to be a really hard problem. And certainly if you were putting something, together for space applications, for example, you would find all sorts of error handling codes built into the hardware, because it's almost, guaranteed you're going to get a lot of these errors. I don't know if you can handle it in software, actually. I mean, within a DRAM, because you'd need to store those extra 3 bits, or however many extra bits somewhere, and if you're not storing them in the memory, you'd need to have a copy of your memory in your software somewhere. So I think it's almost always being done by hardware, but that's just based on my last time I looked at it.
It would be really hard to do it by hardware because even if you're doing it by software, it's still susceptible to getting hit by an alpha particle.
It is, but it's done in a way that if the error bits themselves get perturbed, you can still detect that. Just like with parity, if the parity bit is the one that actually gets upset, you'll still notice that there's an odd number of 1s. But yeah, it's another branch of engineering that it's above my pay grade, as they say. Yeah, those darn solar rays. Other applications, so things like UPCs, Universal Pricing Codes, or ISBNs. These are all numeric codes that, before laser scanners were typed in by hand. So you want to buy, yeah, my sweetie got me M&M's. So you want to buy a bag of M&Ms, right? And when you're at the checkout stand, you're running these in, and you don't have a laser scanner yet. You type this number in, and it correlates to peanut butter M&Ms, and it pulls up the price from a database, right? But it's possible that you make a typo when you type these numbers in, and now instead of a bag of M&Ms, it thinks I'm buying a TV, right? Or vice versa. You're buying a TV, they code in the pricing code and they make a typo, and now for the price of a bag of M&Ms I get a nice 4K TV. So we want to detect errors in these codes. So these things have what are called check digits, and you find check digits pretty much anywhere that you find numbers, credit cards, ISBN numbers, universal pricing codes, things like that. And it's just some kind of algorithm, usually involving simple arithmetic and reduction modulo something to generate these digits. So UPC, for example, and this is not the 11-digit UPC code you normally see. I think it's different for food. But UPC code is basically 11 digits. And there's one digit which gives you the product category, 5 digits for the manufacturer, and 5 digits for the product itself. And the way you generate a check digit, if we call this X1, X2, 3, 4, 5, 6, X7 through 11, you basically do 3x1 plus x2 plus 3x3 all the way up to x11. And then there's an extra check digit. So take this, and I think you just do it mod 12, and that should give you the check digit. And so there's a 12th digit, and it's generated by this, and it turns out if you transpose two of these numbers, you'll get a different check digit. And one of the more common key punch errors is, you want to type in a 25, you type a 52. You transpose. Well, because you're scaling consecutive digits by different factors, this will pick up almost all transpositions. I think it's like a 90% chance that it catches those. And ISBN is similar. You have your digits, you add them up, but you use a weighted sum and you reduce modulo 11. So you can look up details of these online. But that's one thing where we see these things being used in regular life. Alright, so Wednesday I want to start talking about cryptography, and going to talk a little bit about sort of classic crypto systems, the idea of cryptography, why we do cryptography, the idea of securing an algorithm versus securing information, and working towards public key crypto. And we should definitely be able to get through public key crypto by Friday. And that's not something where you need to understand the algorithm. It's a whole nother course to actually understand this stuff well enough to code it. But I want to just kind of like run you through the basics of it and just kind of let you see how some of the things we've been talking about, Fermat's little theorem and modular exponentiation and so on, how these come together to create what's called an asymmetric cipher, something with a pair of keys, public and private, and how that's what makes our internet commerce work today, and why things get so interesting when we figure out how to factor numbers. Alright, so that's 150. I gotta leave at 150 on Mondays because I have another class coming up. But keep working on the homework, come by office hours if you're stuck, and otherwise I will see you next time, and enjoy the rest of your day.
Bye-bye. Thank you, bye.
Alright,
Thanks.
bye.
What is that last piece of the Fermat's little theorem doing the 722? Can you show that screen?
Let's see. That one?
You're not sharing.
Oh, I stopped my share. There we go, that one.
how did it reduce to the 5?
So we leapfrogged up to 7 to the 220 is congruent to 1. That's using Fermat's little theorem. Then we just multiplied by 7 once to get 7 to the 221. Then multiplied by 7 again to get 49, and 49 mod 11 we just had to do by hand. 11 times 4 is 44, and we've got 5 left over to get to 49.
Okay. So I'm missing the why that's all congruent, like 722, 49, and then the 5.
Which part are you missing?
But I'm not understanding that last piece. Like, I get how, like, you got
This piece?
722 is 7 to the 222 is congruent to the 49, but why is it congruent to 5?
Oh, 49 mod 11. So how many times does 11 go into 49?
4.
And how much do you have left over?
5.
That's your 5. Right, so it's congruent to whatever the remainder is when you divide by 11.
And so how does that help us calculate 7 to the 222nd?
Because if 7 to the 222nd is congruent to 7 times 7, which is congruent to 49, which is congruent to 5, these congruences are transitive. So this is congruent to 5. What we're doing with modular arithmetic is sort of just like continually breaking these things down to smaller and smaller pieces. And if we're working mod 11, we can always get down to something, you know, smaller than you know, with just a few digits. Smaller than 11, or maybe, you know, if this was congruent to 10, we might have 10 times 10, but it's, you know, not going to get to be a really big number. And this part has nothing to do with Fermat's little theorem. That's just kind of the definition of congruence. All right, how about think that over, and if it's not making sense, come by office tomorrow. We can talk about it more. All right, see you next time.